Let us consider the particle in a box in 2 dimensions. If we consider the x-axis, the two boundaries are x is equal to 0 and x is equal to L. The particle will not be found into the boundaries, and so at x is equal to 0, the value of the wave function psi equal to 0, and at x is equal to L, the value of the wave function psi is equal to 0. Next we have the y-axis, and it has two boundaries. One is y is equal to 0 and the other is y is equal to L. At the boundaries the particle cannot be found, and so at y is equal to 0, the value of psi equal to 0, and at y is equal to L, the value of psi equal to 0. In the box the particle keeps moving, and moving particle is found in between the boundaries and it is not found in the boundaries. So in between the boundaries the particle can be found, that means the psi is not equal to 0. Since the particle is moving, it will have only kinetic energy and the potential energy will be 0. And so total energy will be equal to the sum of the potential energy plus kinetic energy. Since the particle is moving, potential energy is 0 and the kinetic energy is half mv square, and so the total energy is mv square by 2. The total energy is equal to mv square by 2. Multiply the numerator and denominator by m and we will get m square v square by 2m, which is mv the whole square by 2m. The product of the mass and velocity is known as linear momentum, which is given by the symbol p, and substituting p is equal to mv in equation 1, we get the total energy equal to p square by 2m, and the Hamiltonian operator, which is the total energy operator, which is h hat, will be equal to p hat square by 2m. The linear momentum operator is given by h by 2 pi I dou by dou x plus dou by dou I, since we are considering the particle in 2 dimensions. Substituting equation 5 in 4 pattern, before that we will take the square of p hat, and it comes p hat square is equal to s square by 4 pi square I square dou square by dou s square plus dou square by dou y square. I square is equal to minus 1, and so p square hat will be equal to p hat square will be equal to minus s square by 4 pi square into dou square by dou s square plus dou square by dou y square. Substituting equation 2.8, which is the expression for p hat square, in equation 4, which is the expression for Hamiltonian operator, we get Hamiltonian operator h hat is equal to minus s square by 8 pi square m dou square by dou square plus dou square by dou square. This will be the value of the Hamiltonian operator for the particle box in 2 dimensions. Now let us consider the Schrodinger equation, which is h psi equal to E psi. Substituting the Schrodinger equation, substituting the value of the Hamiltonian h hat, which is equal to minus s square by 8 pi square m dou square by dou a square plus dou square by dou e square, that is equation 9. In equation 10 we get minus s square by 8 pi square m dou square by dou a square plus dou square by dou e square psi equal to E psi. Splitting the terms on the left hand side, we get minus s square by 8 pi square m dou square psi by dou a square minus s square by 8 pi square m dou square psi by dou e square equal to E psi. Now we should remember that we are considering two dimensions. Two dimensions are x and y. The position of the particle depends on x as well as y. So the value of psi will depend upon x as well as y. Value of psi depends upon x as well as y. That means the first term depends upon x and y, and the second term also depends upon x and y. Now we are interested in getting two terms. One term exclusively dependent on x and another term exclusively dependent on y, and for this we make use of the variable and separable method. In this method we make a substitution psi equal to capital X of small x into capital Y of small y. In other words, capital X depends only on x, capital Y depends only on y. In short, psi equal to capital X capital Y, and substituting this equation 13 in equation 12, we get in place of psi we substitute capital X into capital Y. In place of psi we substitute capital X into capital Y. In place of psi we substitute xy. Now if you look at the first term, this differentiation with respect to x, and so capital Y will remain as constant, it can be taken out. If you look at the second term, the differentiation with respect to y and capital X will be a constant, you can take it out, and doing this we get minus s square y is a constant by 8 pi square m dou square x by dou a square minus s square x is a constant by 8 pi square m by dou square y into dou a square y by dou e square equal to exy. Now if you look at the first term on the left hand side, it once again contains x term as well as y term. The second term also contains y as well as x term. The term on the right hand side also contains x as well as y. Now divide equation 15 by capital X capital Y. If we divide by capital X capital Y, this y will get cancelled and we will get a capital X at the bottom. Here if we divide it by xy, x will get cancelled and you will get capital Y at the bottom. What we get is something like this: minus s square by 8 pi square m capital X into dou square x by dou a square minus s square by 8 pi square m y into dou square y by dou a square equal to E. Now what we find, we don't find y here in the first term, the left hand side. That means this is only dependent on x. The second term we don't find the term x. That means this is dependent only on y. So as one term that is dependent only on x and the other term which is dependent only on y. Now the term on the right hand side depends on x as well as y. So we take E and substitute E as a sum of two terms, Ex and Ey. Ex dependent only on x and Ey dependent only on y. Doing this we get something like this. Now if you examine this equation carefully, what we find is that the first term on the left hand side depends only on the x. First term on the right hand side, which is Ex, also depends only on x. The second term on the left hand side depends on y only, and the second term on the right hand side depends on y only. So equating the x dependent terms, we get an equation, and if equating the y dependent terms on the two sides, we get an equation. So equating the first term, which is x dependent on the left hand side, equal to x dependent term on the right hand side, we get minus s square by 8 pi square mx into dou square x by dou a square equal to x. Similarly, y dependent term on the left hand side is made equal to y dependent term on the right hand side, and we get something like this. We have to solve these two equations. That is what we are going to do. First we will solve equation 19, which is dependent on x, and similar procedure will be followed for the equation 20, which is dependent only on y. Considering the first equation, which is dependent only on x, what we have to do is take the all other terms other than dou square x by dou a square, that is the coefficient of dou square x by dou a square, minus s square by 8 pi square mx to the right hand side. We get minus 8 pi square mx ex by a square equal to dou square x by dou a square. Now you have to take the term on the right hand side to the left hand side, and so the negative term will become positive term and the right hand side will become 0, and this is what we get. Similarly, rearranging the other equation, that is equation 20, this is taken to the right hand side. This will become 8 pi square my ey by a square, of course minus. I am taking the negative term to the right side, left side we will get something like this. Now we will solve equation 21. For this, take the second term on the left hand side, and x, capital X is the function. All the other things other than the capital X are taken as k square, and since it is dependent on x, we assume it is k square. You can even take it as k square, it doesn't matter. 8 pi square m ex by a square is equal to k square, and this substitution has to be done in equation 21, and we get dou square x by dou a square plus k square into capital X, the function here, equal to 0. This is a standard form of the differential equation, and the solution for this is capital X is equal to a sin kx x plus b cos kx x. It is the same as saying capital X is equal to a sin kx plus b cos kx, except that kx depend only on the variable x. Now we have to find out the constants a and b in this equation, and for this we make use of the boundary conditions. If you look at the boundary conditions, look at the first slide, we find that the first boundary condition with regard to x is when x is equal to 0, psi equal to 0. This is the first boundary condition, which we will make use of here. In the slide which we have now, if we make use of the boundary condition that when x is equal to 0, capital X is equal to 0, since capital X is a function which depends on x, here x is equal to 0, here x is equal to 0, and this capital X is also 0, and we get something like this. Sin 0 is 0, the whole term will become 0, and cos 0 is 1, b into 1 is b, so b is equal to 0. And if you substitute b is equal to 0 in equation 25, if you substitute b is equal to 0 here, this second term will become 0, and we will get x is equal to a sin kx into x. Now we have to apply the second boundary condition. The second boundary condition is When x is equal to L, psi is equal to 0. We apply the second boundary condition in the corresponding equation. We get when x is equal to Lx, x is equal to 0, capital X is equal to 0. And if we apply this condition here, we get small x is equal to Lx, capital X is equal to 0, and we will get A sin kx Lx is equal to 0. This will be true only when KL is equal to n pi, where n is equal to 0, 1, 2, 3. Of course, since the variable is x here, we get instead of k, we have kx, instead of L, we will have Lx, instead of n, we should have nx. If we have this, we will find that kx is equal to nx pi by Lx. Kx is equal to nx pi by Lx, and we get capital X is equal to A sin nx pi x by Lx. What we have substituted is, instead of kx, we have substituted nx pi by Lx. Now we have to solve for the constant A. This is done using the normalization condition, according to which integral 0 to L, 0 to Lx, you should take it as 0 to Lx. Now the function is capital X, which is dependent only on x star x, dx is equal to 1. And if you substitute the value of capital X, A sin nx pi x by Lx here in equation 32, we get something like this. Remember that this is Lx and not L. And if you integrate it, you will find that A is equal to root 2 by Lx. Now substitute A is equal to root 2 by Lx here in equation 31, and we will get x is equal to root 2 by Lx sin nx pi x by Lx. Similarly, if we solve the equation for y, which is an equation like this, it is equation 22, according to which dou square y by dou y square plus 8 pi square my ey by s square equal to 0. If we solve this equation, we will get capital Y is equal to root 2 by Ly sin ny pi y by Ly. We already know that psi is a function of two variables, x which is dependent only on small x and capital Y which is dependent only on small y. Substituting the expressions for capital X and capital Y here, we will get psi equal to root 2 by Lx sin nx pi x by Lx, root 2 by Ly sin ny pi y by Ly, and this can be rewritten like this: root 2 into root 2 is 2, Lx into Ly, this is the expression for Eigen function for a particle in a box in 2 dimensions. Of course, this is valid only when nx and ny are taking the values of 1, 2, 3, etc. It cannot take the value of 0, because when x or y is equal to 0, sin 0 will become equal to 0 and psi will be equal to 0 and the particle will be non-existent. Now recall that k square is equal to 8 pi square m ex by s square. Rearranging this equation, we get ex is equal to k square, ex is equal to, this will go here, k square s square by 8 pi square m. Kx is equal to nx pi by Lx, that is ks Lx is equal to nx pi, and so kx will be equal to nx pi by Lx. Substitute equation 30 in 39, we will get Ex is equal to n square s square by 8m Lx square. Similarly, Ey is equal to ny square s square by 8m Ly square. The value of energy capital E will be equal to Ex plus Ey. This is the Eigen value. That is equation 40 plus 41. If we do this, we get E is equal to n square s square by 8m L square plus ny square s square by 8m L square. And the common term for these two terms is s square by 8m, and taking this out, we will get E is equal to s square 8m n square by L square plus ny square by Ly square. For the square, Lx is equal to Ly equal to L, and this will be L square and this will be L square. This can also be taken out, and we will get E is equal to s square by 8m L square n square plus ny square. When nx and ny vary, value of energy will also vary. Nx and ny will take the values 1, 2, 3, etc. Now this is the expression for particle Eigen value of particle in a box in 2 dimensions. Now what we find is when nx is equal to 1, ny is equal to 1, this will become 1 square plus 1 square. This will be 2 s square by 8m L square. This is called as E11 because the first one indicates nx, the second one indicates ny. When nx is equal to 1 and ny is equal to 2, n square will be 1 square, ny square will be 2 square, and 1 plus 4 will be 5s square. Nx is equal to 1 and ny is equal to 2, and so we get E12. We denote this as E12. We take E21, it is similar, except that nx and ny are interchanged. Here we get 2 square, and this here will be 1 square, and this will also be 5s square. This we will call as E21 because nx is 2 and ny is 1, and so this is 1. We find that this is also 5s square by 8m L square, this is also 5s square by 8m L square, and so E12 is equal to E21. If we consider both nx and ny equal to 2, we get n square plus ny square is equal to 2 square plus 2 square, and 4 plus 4 is 8s square by 8m L square, and this is E22. Now representing this in the form of an energy level diagram, the lowest energy will be E11 and the next higher energy will be, instead of 2s square, now we will have 5s square by 8m L square, and there are 2 levels which have the same energy we have seen earlier. That is E21 is equal to E12 is equal to 5s square by 8m L square, and 2 levels having same energy, and that is what you call as degeneracy. That is the number of energy levels having same energy. This is doubly degenerate. Degeneracy is 2 levels have the same energy. Next we will have E22, and this E22 is equal to 8s square by 8m L square. And next one is E23 and E32, which will have the same value because this is 2 square plus 3 square, 4 plus 9, 13. This is 3 square plus 2 square. This is doubly degenerate. These two are doubly degenerate, 2 levels having same energy. 2 levels having same energy. What we find is that as we go up the diagram, the value of energy increases.